So, hi everyone, my name is Juba. I'm a PhD student at Caltech. This work is joint work with Yiling, Chen, Nicole, Immorlica, Brendan, Lucier, and Vasilis, Syrgkanis. And most of this work was done when I was interning at Microsoft Research last summer. So the setting that I want to talk about today is a setting in which an analyst wants to estimate some statistic or some statistical model, but the analyst doesn't actually have access to the data himself, so he has to buy the data from a bunch of agents. An example of such a setting could be that the analyst wants to estimate the prevalence of a disease in a population, so he wants to know what fraction of a given population has, let's say, HIV. And the way he's going to do so is the analyst is going to ask individuals in the population to report whether they have HIV or not. So obviously that's very sensitive information, and people are going to incur a privacy cost for telling you whether they have HIV. And the analyst should compensate people for their privacy losses. You could also think of the, well, sorry about that. So you could also think of the analyst as trying to train a learning model, but the analyst doesn't have labeled data, so the analyst goes on Mechanical Turk, asks a bunch of workers to label the data for him, and pays them for their time and effort. And so usually what you would like to do in a setting like this is you would like to get as much data as possible from the agents that have the lowest cost, because you're trying to maximize the amount of data you get for any budget that you have. But in practice, it's often going to be the case that the costs of the agents are going to be correlated with their data. And when that's the case, if you're not careful and you only buy from the low-cost agents, you might end up with a biased estimate. So back to the HIV example. People that have more sensitive data, so people that actually have HIV, will have a much higher privacy cost for revealing that information. And what that means is that if you only buy data from the agents that have a very low cost, you're only going to buy data from the people that actually don't have HIV in the population, and your final estimate is going to be really biased. In the learning setting, you could imagine that the cheaper data is lower quality and is going to introduce more bias than higher quality data. And so basically, the assumption that we make in this paper is that the cost and the data of the agents are correlated, and that this correlation is completely unknown to the analyst. So as I was saying before, intuitively you still want to buy as much data as possible from the lowest cost agents, but also get an estimate that's unbiased. And there is a way to do so. The analyst can use what is called the Horowitz-Thompson estimator. What it is basically the unique, unbiased linear estimator in settings in which you want to estimate the mean of a population, and you have different subpopulations, and you sample data from these populations at different rates or with different probabilities. And the way it works is basically going to reweight the data points of every single individual that you're buying from as by 1 over the probability of sampling from the subpopulation this data point is coming from. What this means in our setting is that if I buy data from low-cost agents with a much higher probability than from high-cost agents, I should put a higher weight on the data of the high-cost agents so that my estimate is not biased towards the data of the low-cost agents. Now that we have this unbiased estimator, one thing we would like to do is to make this estimator as accurate as possible. And because it's unbiased, you can just see optimizing the accuracy of this estimator as minimizing its variance. So now let me tell you the full picture, and so what our model is. But before I do so, I would like to point out that the model that we're studying has actually been introduced and studied before by Aaron Roth and Grant shown back at EC'12. So in this model, we have n agents. Each agent has a data point and has a cost for producing or revealing this data point. And we assume the data and the costs are taken from a joint distribution. But this joint distribution is not fully known to the analyst. So as I mentioned before, the analyst doesn't know the correlation between the data and the cost of the agents. However, we do make the assumption that the analyst knows the marginal distribution of costs. Now, the analyst is trying to compute an accurate estimate via the Horvitz-Thompson estimator of the population mean. And here, the way we measure accuracy, as I mentioned before, is in terms of variance. But the variance of this estimator depends on the underlying distribution of the data that is completely unknown to the analyst, so the analyst cannot optimize that metric. So instead, we're going to make the assumption that the analyst is going to optimize the worst case variance, where the worst case is taken on the unknown correlation between the costs and the data. Motivation for doing so is robustness. If you do this, you're guaranteed that your estimate is going to be accurate no matter what the correlation is. And the analyst has a limited budget, so the analyst is not going to be able to buy every data point from every agent. So what he's going to do is he's going to run a survey mechanism that is going to decide which agents to buy data from and at what price. And the problem in this paper is to design this survey mechanism. So here is how the mechanism is going to work. First, the mechanism is going to ask agents to report their costs. And here we make the assumption that the agents are strategic. They're trying to maximize their utility. So they may decide to misreport their cost to the mechanism if they get more utility from doing so. However, we make the assumption that the agents are not going to lie about their data, so somehow the data is verifiable. And once the mechanism has elicited the costs of the agents, the mechanism is going to buy from each agent with a probability that's given by the allocation rule, which is just a function of the reported cost. And if you buy from an agent, you have to pay this agent according to the pricing rule. The goal of our paper is to design this allocation and these pricing rules in order to optimize the worst case variance under a constraint on the budget. And so our results are that we are able to characterize exactly what the optimal mechanism is in this setting. And that's a natural next step from the work of Aaron and Grunt, in which they give a near optimal mechanism for this problem. And when I'm telling you that we're characterizing exactly the optimal mechanism, I'm not telling you that we're giving you an efficient algorithm to find this mechanism. We actually derive what the allocation and the pricing rules are in closed form. And finally, we see that like this mechanism, and in particular the allocation rule, exhibits some new and interesting structure. So let me just jump to the structure of the mechanism. So here I'm plotting the allocation rule as a function of the cost. As you would expect, the allocation rule is going to be non-increasing in the cost, so that's following our intuition from the beginning of this talk, which is that you want to buy more data from low-cost agents and less data from higher-cost agents. But what's really interesting here, and what's really new, is the fact that there is a pooling region here in which you're going to basically pool all of the low-cost agents together and buy from all of them with the same probability. And then past a given threshold, the allocation rule is going to be decreasing in 1 over square root of the cost, roughly, the agents. So the reason this is new is because under the assumptions that we make, and I'll come back to this later, the solution of the paper of Aaron and Grant, their near optimal solution, is actually strictly decreasing and doesn't have this nice structure with a pooling region. So one last thing that I would like to point out on this figures is that, so if you look at the line, so like the blue line is the highest budget line, the red line is the lowest budget line, so each line corresponds to a different total budget for the agent. And the size of the pooling region is actually going to be decreasing as the budget decreases. So now that I've told you the main result, let me just say a word about the techniques of this paper. So what we have is a mechanism design problem in which we're trying to optimize the worst case variance of the Horowitz-Thompson estimator under constraints. And so we have mechanism design constraints. We want the mechanism to be truthful and individually rational. So we want people to report their true costs to the mechanism. And we also want people not to have any incentive to opt out from this mechanism. The other constraint that I've mentioned several times already is the budget constraint, and we want to make sure that the expected payments of the mechanism to the agents are going to be at most the budget of the analyst. Now, the way we deal with this mechanism design problem is that we make a regularity assumption on the costs. Doing so allows us to reduce our mechanism design problem to a simpler convex min-max optimization problem that does not have any of the mechanism design constraints anymore. And once you have this convex min-max problem, you can just see this problem as a two-player zero-sum game in which the objective and the action spaces of the players are convex. And so here is how the game is set up. So the two players are the analyst and an adversary. And the adversary is controlling the correlation between the cost and the data, and is trying to make it as bad as possible for the analyst. So it's trying to maximize the variance in terms of this correlation. And the analyst, on the other hand, wants to minimize the variance and is controlling the mechanism, so more specifically the allocation rule under a bunch of constraints. Remark here that I'm telling you that the analyst is controlling the allocation rule, and I'm not saying anything about the pricing rule anymore. That's because once you make the regularity assumption on the costs, the pricing rule can be expressed as a function of the allocation rule, and you can replace everything with the allocation rule in the optimization program that we're solving. And so once you have this zero-sum game, so if you want to find an optimal solution for the analyst, you just need to compute an equilibrium of this game, which is algorithmically an easy problem, but I would like to point out that we're not just giving you an algorithm to solve this problem. We're actually finding the solution in closed form, which requires a lot more work and is not trivial and is pretty much the bulk of the paper. Finally, I would like to tell you about the main extension in our paper, which is that we extend our results to the case of linear regression. So now the setting is that my data points are going to be pairs of features x and an outcome y. And this outcome is going to be a noisy linear function of the features parameterized by some unknown theta, and that's what the analyst is trying to estimate. So this problem is slightly different from the one we're solving before. Before, we were just computing a weighted mean of the data points of all of the agents in the population. Here, our estimate is different. It's minimizing some loss function, where the loss function is some importance weighted version of the mean squared error. And so because we have a slightly different problem, we also have slightly different results. So the results have the same flavor in the sense that the allocation rule, the optimal allocation rule for the mechanism is going to exhibit a pooling region and a decay in 1/√of the cost outside of this pooling region. The difference, though, is that the pooling region is not going to be for intermediate costs. So the allocation rule is going to be decreasing, then there's going to be a pooling region, then it's going to be decreasing again. So basically, what we've done in this paper, just to summarize everything, is we've studied the problem of buying and aggregating data from a bunch of agents when the data and the costs of the agents are correlated. what we do is that we provide an optimal mechanism in closed form to solve this problem and optimize the accuracy of your estimate under a budget constraint. We show that our solution is exhibiting new structure on the form of the optimal mechanism, and we extend our results to the case of regression analysis. And that's all I want to talk about today, so thanks for listening. Yes?
Well, you can apply the technique to the problem where you have people who label the data, and they have different preferences of labeling the data. For example, I'm better in labeling pictures. You're better in labeling web search results. So the question is, in this setting, you also can have different side of agents, which are companies that want to their data label, and they also can submit value to the cost for their work.
Price.
Yes, price. So maybe there is an easy way for reducing this problem also to your result when you have two sides.
Sorry, I'm not sure I understood the question. So
can you apply this technique
yeah.
to the problem when you have two sides? And they also want to misreport their costs.
Well, I mean,
their price. So they want to lower it.
So we haven't thought about this. I think you can, in the sense that so basically you could, if you're trying to look for an equilibrium, and in this equilibrium you can figure out what the distribution of cost is going to be, then you could apply our techniques. So. But okay, so I'm not 100% sure what you mean. So what do you mean by having two sides? Do you mean by you also want the companies that are labeling the data to be able to somehow manipulate their costs?
Yes, but this is not the very relevant example because, well, you took as a basic example the data, for example, acquisition. And here you have just people who manually label the data, which is slightly different.
Right.
Yes, so of course, if you want to make a market where there are companies who want to label their data on some price, and there are people who manually label the data, you're kind of thinking of a second side. You want them to be truthful when they choose what bunch of data they label. The second side is to make such a rule that the companies also will submit truthful price for the data label.
Right.
And, you want them to do it with a good quality, I guess, and for low cost, making some.
Right. Okay. I see. So okay. So the assumption that we're making here is that the distribution of costs is known. So in particular, you know what the support is going to be, and once you know what the support of the cost is going to be, our mechanisms are truthful, so we can ensure that people are not going to misreport their costs. We don't have any guarantee when you actually don't know what that support of the cost is going to be, which is, I guess, what's happening in your setting, in which basically the companies could be completely lying about like what the possible costs that they have are. So yeah, but